Hi, time to take a look inside another bit of interesting kit today. What we've got today is this. This is a display panel from a large outdoor LED display screen. And actually not just any screen, this actually came from Piccadilly Circus in London. They just had a new screen put in for the Olympics, and thanks to Tom at Display LED, I've got a piece of the old one to have a look at. Here's a close-up view of the panel. You can see it's made of separate red, green and blue LEDs. The other thing you notice is that the LEDs are actually oval in shape. Now the reason for this is most screens want to have a fairly wide viewing angle horizontally, but will be pointed at a specific direction. In this case, because this was designed for a high up mounting, you can see the LEDs are actually pointed downwards. You've got these bits of plastic here. These are going to be a combination of shading to avoid if sunlight hits there, it's going to reduce the contrast, but also probably helps keep the water off as well. This section is actually of a fairly similar size to the Jumbotron module. The size of these sections are sort of there's various trade-offs involved in the design of these things. One of the major ones is that each module really needs to be liftable by one person for maintenance, because somebody could be on top of a cherry picker or need special access to get to it. So for maintenance it's really necessary, sort of like for one guy to be able to pick up and take out one module. Although in terms of cost you might be able to do it cheaper if you had larger modules. The practicalities are really that you've got to be able to replace them without needing sort of several people to do it at once, or a crane or anything. Right, around the back of this you can see there's some sort of big heat sinks for power dissipation, and there's also two connectors. And what I've actually got here is the control system that controls 4 of these tiles to produce each of these modules actually has 3 16 by 16 tiles in it, and this control system and power supply runs 4 of these to produce a 48 by 64 pixel overall display section. Right, this is the power supply box. We've got 2 of these massive great 5-volt power supplies. Each of these can supply 5 volts to 50 amps. One thing I was surprised at when I pulled the lid off here, they're not actually screwed in. But in fact, if you look, there's actually some locating pins there, and in the lid you've got some sort of big lumps of rubber to hold them in place. Now on a system, pretty much any system, the power supply is one of the things that's most likely to fail. So obviously they've done that so it can be really easily replaced, because bear in mind this is going to be screwed to the back of the unit, so access isn't going to be particularly great. So there's 2 5-volt supplies for the display. This is a 12-volt supply. This is basically just for the fans. There's internal fans in here, and I believe there may be some external fans, because there's a mention somewhere of there's one of the labels here, it says to fan duct, so I'm guessing these things are probably mounted in a duct that passes air across these heat sinks, and there's maybe some external fans to pass air throughout the whole assembly as well. Down on this board here, I'm not quite sure, I think these resistors may be for current sensing of the fans. All this is to do with all the cooling control. There's actually completely separate circuitry and separate connectors for all the fans, and this thing will actually work without any of this switched on. And we've got the 5-volt supplies go through this board, and what we can see here, there's actually a couple of current transformers. So this is going to be monitoring the actual amount of current being drawn by the displays. Right, the other box controls all the data processing. So on the back we've got a mains connector. I didn't have the plug for this, so I've just soldered some wires on there and heat shrink them over as a quick fix. We've got data in. This is a high-speed digital data stream which will come from a processor that does all the video scaling and other processing, and there's 1 in and 2 out, so this data gets distributed over all the panels. And there's these data connectors, and this is to do with the system monitoring, particularly things like fan monitoring, temperature monitoring and so on, and that's an RS422 bus. Inside this box we've got 4 main boards. This is the first one. This takes the digital data input from this data stream and basically formats it. This is essentially a very fast serial to parallel converter. This outputs a parallel RGB data stream that's then processed by the rest of the system. There's this high speed, it's basically a very high speed serial to parallel converter, which gets very, very hot, especially as this fan seems to have gunged up. Data then goes through this ribbon cable to this first board. Now this board is in charge of processing the brightness data, things like dealing with the calibration of the screens. Each of these screen tiles has got an E² prom on the back which holds all the calibration data, so that when they build these they actually test them to measure the actual intensity of all the pixels, and they store that in that E² problem, so that when the system starts up, this board actually reads all that data and can then do intensity correction to get uniform brightness over the whole system. But this also does things like gamma correction and other general brightness processing, and some switches here that enable various test modes. And there's a status indicator here, so when it starts up it goes through various status things, just giving you the various status. All these boards have got various test modes, because obviously on a complex system like this, if you've got a fault, it's very important to be able to track down the cause of that fault quickly and easily. So there's at each stage of the process, and there's various test switches that can generate test patterns, and there's these status indicators, so you can quickly at least figure out down to board level where any problems might be. And there's some quite a lot of flash memory here, and these are used for storing all the intensity correction data and the like. There's some RAM there used for various processing, 2 big Altera FPGAs. This board's also responsible for selecting which part of the image to display. You've got these address switches here, which are actually in little connectors. So I'd imagine in some versions of this product this is probably on some sort of external switch. There's just an internal board that sits on there, and there's just row and column numbers, 4 bits for each, so it looks like it allows up to 16 rows and columns. So this section, this four module section, can be part of a large display with up to 16 rows and 16 columns of these units. When it comes out of that board, the data then goes to this board. This generates the low-level format for the actual LED drivers. There's not much intelligence in the tiles themselves. It's basically a huge bunch of individual LED drivers. So we've got a big FPGA here which will be taking this data, shuffling it around to the right, so it's all the right way around, formatted, and then we've got these drivers. Interesting, they use just standard 74HC 240 as drivers. It's not a differential bus or anything, because these boxes are designed to mount very close to the display, so the cables are only about 1 metre long, so it's not having to drive big long cables. Although it's there's several serial streams going down each cable, but there's not a huge number of connections, but it's not long enough to really justify going to a differential signalling. You've got these ferrites around the cable just to avoid noise radiating off these cables, because obviously the cables will act a bit like an antenna. One thing I was a little bit surprised at, although they've got sort of these sealing glands here, and the connectors, and these connectors aren't actually sort of IP68 rated or anything. This unit itself is actually pretty well sealed. I'm not sure, I'm guessing that the idea is that this is in a semi-sealed environment at the back, because these aren't fully sealed connectors, and they've got some adhesive heat shrink on here, but this is just sort of semi-open braided sleeving, and this is actually going through these cable glands. And in fact, I did actually see there's a little bit of sign of some water damage on there. There's just a few traces of water. I mean, all these boards are conformably coated. You can see they're a bit shiny, so there's a little bit of moisture protection on here, but obviously for an outdoor system, water is one of the major enemies. There's this little board here. All this does is control things like temperature and fan, so it's got connections to the tile cables, and this will be fan and temperature monitoring inside the tile. There's some connectors here. One of these goes to that board we saw in the power supply with the current transformers. So this is all just to do with fans, fan monitoring and general system monitoring, and it will actually work without this connected at all. Let's take a look inside this LED module. This is very well sealed. There's actually silicone all around these heat sinks. You can actually see it sort of splurging up through the holes. And we've got a nice chunky rubber seal all the way around here to the front. And this is all the sort of welded steel construction, so this is very nicely weatherproofed. The boards are all conformal coated inside as well. You see we've got heat sinks on the back with these fans, and there's the LEDs in the driver boards below, so obviously for an outdoor thing you don't want to have any external airflow, so these fans just circulate the heat through the internal air from these boards up to the heat sinks without needing any external airflow to let in water and dirt and general gunge. Apart from the LED tile boards at the front, there's not really a great deal to see in here. There's a little board here, which I think this is just a junction board for the various internal monitoring, fan monitoring and so on, so all the fans plug into this board. There's a whole bunch of status LEDs on there. Yeah, there's a chip on there which is actually an E² PROM, and that's probably got information about the unit serial numbers and so on. Each of these tile boards I'll take a closer look at, but those got an E² PROM as well for the intensity data. There's a little board here which is a temperature monitoring board. This all runs on I²C for the monitoring, so there's a temperature board on the heatsink, and there's also another one on there to show the temperature of that top tile. and other than that it's just power wiring. This is all 5V, pretty high current. They're using multiple separate strands rather than one big thick cable, because big thick cable it's just a bit unwieldy, it's not really flexible enough. So the other limitation was the connectors they've used. They'll only take up to a certain cable size, so they're obviously, this wire is obviously the biggest that would fit in there, so they've just split it into multiple parallel cable feeds. They're all actually electrically connected together. Surprisingly, these are actually joined with solder and heat shrink rather than crimp terminals, which must be fairly labour intensive, but these are just teed off and plug into the interconnectors on the tile board. And there's a ribbon cable for data. This goes across all boards, and there's some address selection switches here to tell it which of the 3 tiles it is. Right, this is the actual tile module, 16x16 RGB module. On the back you can see it's made up of these vertically mounted driver boards, and there's the front board that's actually got the LEDs mounted. You can probably see it's quite shiny because it's got a thick layer of conformal coating on it. The front board's got pretty much the only thing it's got is LEDs. There's a few 220 microfarad tantalum decoupling caps on there, but not really a great deal else. These have just got 16 channel drivers, one per LED. There's 2 versions of these. There's the master board here, which connects to the ribbon cable. That's got an address selection. It's also got adjustments to fine trim the red, green and blue current for all the boards, and the other boards have literally just got the drivers. These appear to be sort of butt soldered onto the main board. I can't see if those go through or if they're just held horizontally and then just a solder fillet to join them onto the PCB. And obviously there's going to be data tracking on this board to pass the data from one board to the next. And here there's the power inlet here. There's some little inductors to suppress some RF interference, and you can probably see the LEDs are actually soldered into the board at an angle, so the LEDs themselves are, you can see they're angled, and the leads as they come through the board are actually angled. Just unsoldered one, these, to look at the holes, they've used fairly big holes. That allows the LEDs to be placed in at an angle. They haven't done anything clever like actually drill the PCB at an angle or anything. They've just made the hole big enough to be able to tilt it, and I'm sure they probably use some sort of mechanical assembly jig to get everything lined up properly. Just take the front off of this. You can see what they've done, they've actually potted the entire front for waterproofing. So obviously this is the most critical part for the weather sealings. This is actually exposed to the outside. Obviously they could have put, say, a plastic sheet over the front to provide waterproofing, but the problem is that then gets dirty, you get glare off of it, and it reduces the light transmittance. So the LEDs themselves are actually directly exposed, and then they're sealed at their base. This whole thing is just potted. This whole frame is like a fairly chunky aluminium frame. There's a nice sort of gasket in there to seal it when it's all screwed together, and it's clamped in about 5 points along each side, so it's very solidly mounted and very well sealed onto its mounting base plate. Again, you can see the angles of the LEDs. These ones use the sort of fairly conventional 3 LED RGB. I noticed on the on this they've actually got sort of almost dummy LEDs there, and if you look on the back there's some little marks which suggest that their mould tooling can probably actually have all 4, because I've seen some LED tiles that actually have 2 reds per pixel. It may just be that they're old ones and the red LEDs weren't quite as efficient as the other colours, but I don't quite know why they've actually got these little dummy pretend LEDs on there, unless that's just part of the way they do the moulding. It's the way their moulding system works when they're only doing 3 LEDs. I don't really know enough about moulding to know the answer to that one. So close up of this master board. There you've got the E-squared prom. This is basically what they do is when they manufacture these, they give them a burn-in test, then they measure the light output and store that data into this E-squared prom, so that the the controller board can download all the information from the tiles and make corrections to the intensity to give an even light output over all the tiles, regardless of the manufacturing differences between LEDs. Right, here's a detailed analysis of how this thing's actually driving the LEDs. There's a few quite interesting techniques here if you building your own LED displays, so we'll go through it in quite a lot of detail. These are the basic control signals. The latches in this display, they're basically a shift register plus a latch with constant current output drivers, so they're very similar to things like the 74HC595, for example. You shift a load of data into it, and then when you pulse the latch signal, that then outputs all the data simultaneously. And in addition, these have got constant current output drives, so they'll control the lead current regardless of supply voltage. We've got just set up here showing a test pattern, and here are the basic drive waveforms. I've not shown the clock because that's basically constant, but we've got the data being shifted in here for one of the colours. We've got a latch signal. The other thing we've got here is an enable. So what happens is it shifts the data in, latches it, so at this point all the output's ready to display, and then when the output goes low, that actually lights the LED. So here, when this goes low, this is the actual LED. This is actually one of the ones towards the left hand side, somewhere, a blue one, lighting up. So you can see the actual data shifting across. So you can see, for example, that the shift registers on this are set to basically go to sort of top to bottom. The actual format of this data will depend on the actual physical arrangement and connection. That's not something that's you need to worry about too much. So this is basically doing what's effectively a monochrome display. The LEDs are either on or off. One of the problems with a video display is you actually need a lot of grayscales. Not only do you need enough grayscales to show the video content, but because these things are compensating for the variations in the LEDs, they need to actually be able to have fairly fine gradations to be able to balance all that out. And in fact, looking at some of the documentation for this, it does 13 bits of video grayscale. And in addition to that, it does 96 intensity levels on top of that, because there's global intensity control. Again, for an outdoor LED screen, it's probably going to have an ambient light sensor that adjusts the output depending on the ambient light level. Fortunately, on this system, I can actually control the intensity and the video data separately. So this has actually got a test mode which will cycle the brightness up and down. So just enable that. So what this is doing, this is starting off bright and then going narrower. And what you can see now, the way it's doing that is by controlling the length of this enable pulse. So for the bright levels, it's giving a really long enable pulse, so it's turning the LEDs on for quite a large proportion of the time on each of these subframes. And it's doing a really narrow pulse when it gets dimmer. If we just zoom out and look at the whole frame of data, this is 60 frames per second, so this is one complete frame of video data. But what you see is you've actually got multiple of these latches. There's actually about 270 latch periods per frame. Now, you might think these just use sort of simple pulse width modulation. The problem with that is because the drivers are simple latch drivers, they don't have any internal PWM capability, unlike, for example, devices like the Texas 4951, MacroBlock 5031, which actually do the PWM at the driver level. You actually have to shift the data, so you've basically just got an on-off display on the LEDs. Now, if you wanted pulse width modulation, simple pulse width modulation, where you alter the width of the on time to control the intensity, if you need a high resolution, let's say for example we need 12-bit resolution, that would mean that you need to shift 4096 subframes per frame, so actually, because obviously every LED could have a different intensity, so you need to be able to produce a different width for every LED. Now obviously that can get a bit ridiculous in terms of the data rate, so there's a couple of techniques used. One is this adjusting the pulse width to control the global intensity, but there is actually another method being used, and that's to alter the pulse width within each frame as well. Let's take a look at that. Right, we've got a simple flat pattern cycling through the brightnesses here, and if we actually start looking at this in detail, we can actually see there's actually another two types of modulation occurring here. The first is that on every other subframe the data is high or low, so we've initially got basically a 50% brightness by just alternating the data from one subframe to the next. So this is about 16 microseconds per subframe. So that's our first level of modulation, so we've already got another level of brightness control, and obviously the scope for it to do more. And because this is about 16 kilohertz, this isn't going to cause flickering. And in addition to increasing the brightness resolution, the other important thing is not introduce flicker. For example, if this whole panel just had a simple PWM at 60 hertz, it would just flicker like hell. But also you'd get massive current surges through the power supply. If you're turning, several tens of amps worth of LEDs on and off at 60 hertz, then your power supply is really not going to like it. So this is the first level of modulation. But the other one we see, which is actually quite neat, but also very applicable to even simple microcontroller based systems, is these enable pulses that we saw before. Now obviously we've got it's adjusting the width of the enable pulse to adjust the global brightness, but that's not actually the whole story. If we start looking a bit further on, not all the enable pulses are the same length. Right, so here we see these enable pulses getting shorter for the dimmer brightness, but every so often what we see is different width enable pulses. So what's happening here, it's doing, most of the enable pulses are getting the majority of the brightness value, but what it's then doing, it's using these little short ones just to give that last little final tweak. So obviously you could turn the data on or off selectively on these short pulses to actually give a fine tune. So you've effectively got non-linear steps for a short section, so you can get, let's say for example, 8 bits of intensity data via normal methods, and then you can get another few bits by just giving those tiny little short pulses to fill the gaps in. It does these about 3 times per frame, so at the very lowest level you may get a very slight ripple in intensity, but that's not going to be anything like as noticeable as if you were doing a full PWM of the whole thing. And this is a technique that's very applicable to even like dimming individual LEDs on a microcontroller. If you run out of steam for doing software pulse width modulation, you can do a rough PWM to get most of the brightness, and then just do a few little short pulses that you can then fine tune it. I'll just change it back to a test pattern which is now fixed brightness, but with a very slowly changing grayscale. And what you can see here is that it's selectively, in this area of the fine pulses, it's selectively turning on and off the LEDs as it cycles through the grayscale. And again, if we zoom out, we can also see that it's selectively turning on and off on the normal brightness pulses. And it's also, notice it's also interleaving. It's not, for example, just doing it for the first half and then not the second half. It's doing every other pulse, this again to minimise the ripple, so this variation in intensity is distributed throughout the whole frame. So you see as it's getting brighter, it's gradually filling in more and more pulses. And it's doing the same thing, except that it's taking into account the fact that let me find them, that the thin pulses have basically a different weight. There we go. So although our basic intensity pulse is about 5 microseconds, the finest ones, we can actually measure them, they're down to extremely short pulses. I mean, those are about 100 nanosecond pulses. So by just changing the width of that enable pulse, it's getting, you know, a really huge range of brightnesses. It's probably of the order of sort of maybe 18 bits of brightness control without flicker. Here's a quick view of the actual clock and data waveforms. So you see the clock's at about 12 megahertz. So yeah, it's not having to use ridiculous clock rates to achieve all this. And of course, it's got to stick this down a ribbon cable. It's only using single-ended HC TTL type HCMOS buffers. So you can see the waveform's not, it doesn't look beautiful, but it's, you've got a nice clean data pattern here. So to do the full RGB display, it's basically just got 3 data lines, one for RGB, one clock line, but it's still managing to do sort of 18 odd bit intensity resolution down about a metre or so of ribbon cable. So yeah, they've used this modulation technique so that all the data rates stay fairly sensible. You don't need ridiculous numbers of cores in the cable, but you still get decent frame update rates and good intensity resolution.